Welcome back, and this is it though. This is our final get together beyond our finals week demo day. Kind of a bittersweet moment, but it all things have to come to an end. So we can't just keep going forever. I think everyone is generally in sync with what our plans are and how our semester is ending. But just to get it on tape and be make it very official, our final demo day. The next time we will see each other, at least outside of an office hours, uh, will be next Thursday, and I always double, triple, quadruple check the time. I'm pretty positive it's next Thursday at 9:30. So starting at 9:30, we can use the same Zoom session, so connect as normal. The difference is because it's that final exam session, we do have, I believe, the full 2 hours available for our class. I may reach out to a couple teams and generally reach out to see, how catastrophic would it be if it's 2 hours and 15 minutes. I know we can't just keep going indefinitely, but to look at that and say, what is our actual upper limit on time here within reason? Um, because it's just the same math as what we've been doing for all of our demo days. So we do, in this case, need to get to all 8 teams, give each team a similar amount of time, and to be fair to all teams. And there's, of course, more things you've been working on, more, teams won't be able to say, well, we did exactly what the previous group did for this part because you won't have that for your demo. So it'll have to take a little bit longer. And likewise, um, I want to do this peer assessment as part of it. I think it's best to do it live, but I will consider the alternative of not doing the peer assessment live and just doing the presentations live and having the peer assessment being this kind of final offline thing that you're doing. So what will happen is you will have your slides. We'll do Google Slides like before. You'll give your regular presentation and discussing the fun things, demo what you can demo, and then I will ask each team to bring up their own rubric from the project proposal slides. Bring up your own rubric and do a self-assessment. Be honest as best you can. Here's how we think we did. Great on this, really failed on this, overall decent, right? And give yourself a score. It's just your own personal self-assessment. I am then going to have a survey instrument using Google Forms or Qualtrics, I'm not sure yet, where everyone else in the class will also do that assessment of your team's project. Just based on their opinion, probably a fairly snap judgment. We won't have time to spend, 15 minutes or even 5 minutes, really thinking very deeply about the assessment of how you did on a particular part. And that will serve as part of your final grade for that project, with the other 50% just being my own, hopefully somewhat deeper assessment on it. So that is a lot to get done in the time we have next Thursday. So I'm still open to suggestions, but I'm also going to consider not doing that pure assessment live and just pushing that as a, kind of beg each person to get that done reasonably at some point later that day, hopefully no later than that Friday of next week. Because it's 8 teams as always, and if it's 120 minutes, we're still kind of having to keep things pretty tight. Whereas I know teams would want to talk about a lot of things that you accomplished, or the struggles you had, or the bugs that you face, whatever you want to talk about. We'll still have to keep things pretty timely. So that's the plan for next Thursday. It should look a lot like a regular demo day. Um, it's just during that final exam schedule, so we have more time available to it. Any questions about that before we jump back into really the end of the semester here? It's good to see some more faces today. That's group four. I can't tell. You look very casual. Is this on the big screen for group four? That's wonderful. And Micah, I don't think I knew what you looked like, to be honest. So it's nice to meet you, and see you. But um, yeah, that's great. Well, I'm looking forward to this being my final, I guess, outside of potentially next Thursday, my final virtual class, hopefully forever, and very much looking forward to in-person instruction again and all that. But okay, so where we left off on Tuesday is we were just starting to dive into some of the mechanics of CUDA and what that means in practice. And the basic layout of your structure of a program is roughly the same, no matter how many advanced features you're using or how basic it is the application that you're running. So there's generally some sort of memory management that happens beforehand. So it doesn't look so different than the calls that you would be used to for traditional, usually C-based memory management. Um, but those are done beforehand to make sure data is residing physically where it needs to be. We have to be a bit more cognizant of where our data is being placed. Then there's the actual kernel launch. I've showed a couple of examples of it. We'll go back to the syntax of what that looks like. It's not complicated in terms of syntax, but in terms of the model of computation, as we've talked a little bit about, what your organization of threads is sort of the critical challenge associated with launching a CUDA kernel. Then there's usually something afterwards. So we wait for the kernel to complete. We do some additional memory management generally. The kernel was launched to generate some results. We have to get those results back. So that's that step three. And then there's all sorts of newer features that kind of add some tweaks to our basic flow, like you can do dynamic memory allocation inside a kernel to some extent. There's this unified memory model that is more of a syntactical change, but in terms of the programmer's view of memory, really does simplify how we do things. In terms of that memory organization, explicitly there's these different memory spaces for the CPU and GPU. Physically, you can just think of that just like how we think of it for our driver infrastructure. We have DRAM on the workstation, we have DRAM on the GPU, in this case on our FPGA and our lab infrastructure, and we have to have some mechanism to do those explicit copies. Generally, in CUDA, the CPU code is doing the management of the GPU device's memory. The CPU is still in charge. The GPU is still just effectively a co-processor to the CPU. So the CPU is doing the allocation and the freeing and the explicit copying. That is changing with this unified memory model. It's really just changing from a syntactical perspective, ultimately. The semantics of what we're doing, in which we have memory and it has to ultimately be explicitly copied from one device to the other, is still happening. The newer features allow you to not have to think about that as much. The performance implications are still there, but we can just now have things like nice shared pointers, that there's a pointer that the CPU sees and the pointer that the GPU sees, and you don't have to have as explicit of a copy operation happening. It's still happening in the driver space. We're just not having to do it as a programmer. And part of the reason we care about all of this memory management and the methodologies for that is that the bandwidth that's available to us is really significant. This was an example that we ran sort of, I think, on the first day of the semester, where we just looked at uh, the throughput available. This is on a Maxwell class device. In going from device to device, host to device, and the bandwidth that was possible back and forth. And these numbers, although not as significant as if you buy the latest and greatest, incredibly overpriced hardware that's out there, are still really impressive in terms of our memory bandwidth. So that host to device memory bandwidth, that's in bytes. There's at 12.4 or 12 point something gigabytes per second. That's a pretty significant amount of throughput that we have available. So that's not something that's GPU specific. That's due to the PCI Express connection between the CPU and the host and the device card that we have there. But then the actual device to device bandwidth, that's copies from GPU memory back to GPU memory. That's also really impressive. That is a ton of throughput we have available. We talk a lot in 381 about the difference between throughput and latency, and that's still very much the case here. So what I was talking about on Tuesday, which was we have to have these mechanisms to hide memory latency, that is still very much the case. The difference, though, is we can do that and we can still then take advantage of the very large amounts of throughput that are available, right? It's not always the case that those two considerations, design considerations, are in opposition to each other, but it just seems that is often the case, that we can build protocols or buses or interfaces to memory that have very high throughput, but the trade-off is the control logic to do sort of non-sequential access leads to very high latencies. So both those things could be simultaneously true. We have a device that in theory has a huge amount of throughput available to us to read and write from memory. At the same time, we have a device in which doing any individual access to memory in isolation incurs a very large latency. The CPU, traditional CPU microarchitectural solution to that problem is lots and lots of cache. DRAM latency is bad. We're going to avoid it as much as possible by putting as much cache as possible on the device so that it's very infrequent that we actually have to pay that full penalty. And not just amounts of cache, but the types of cache and different approaches to buffering and things like that. But basically, cache is the solution for the CPU world. In the GPU world, what we talked about on Tuesday is still very much the case. There's cache, not nearly as much, but there's still cache. What there is just large numbers of threads, and we're talking to thousands to hundreds of thousands here. And so we hide that huge latency while still taking potentially advantage of that large amounts of throughput by just ignoring that latency, by hitting that latency, feeling that latency from an individual thread's perspective. Your individual thread does a load, it's going to wait 400 cycles until it actually gets the result back if the value is not in cache. But we hide that. We either amortize it or just hide that latency because that thread is feeling it. We have enough threads so that someone is still available to get its work done. The GPU, the streaming multiprocessor core, stays busy because there just happens to be enough threads that there's somebody who's left who still has valid work to do. Somebody's memory request comes back as valid. So I gotta tell you, group 4, I feel just nervous that like I have an actual audience now. That you're just kind of sitting back, like this is Netflix for you, and I don't know how well this compares to Netflix. So that's my main concern I have right now. That you're just sitting back. I feel like I'm being judged by a panel, um, but that's fine. So every so often, just nod approvingly, and even maybe every so often, ah, wow, and you recognize that you've just learned something significant, and that's what I need from you if we're going to be doing it in this mode. Otherwise, I'm just going to move you over to the side so I can't see you. That's the other approach I'll try here. There is a lot of runtime framework components to deal with. A lot of these are optional. So when you look at the whole entire software stack for doing GPU compute, it can actually be a little bit overwhelming. But you're not really required to use any or effectively all of these in any given application. The primary thing is the CUDA call. So all those functions that are prefixed with CU or CUDA for the runtime API, those are the ones you would generally use. And then there are a lot of provided libraries. This is almost always the case that if you're using a language or a programming framework or library that has some provided calls and some middleware to do common tasks for you. This was one of the takeaways when looking at like a memset call in 381. It's very hard to beat memset in terms of performance of initializing a block of memory. That code has been looked at by many people. It's been optimized fairly intelligently. We could write our own memset in a very simple for loop. Getting the performance of a memset would take potentially weeks to months of work. Uh, and so, if we have those libraries available, there's no requirement that you use them. But for example, for the CUDA FFT library, I don't know that much about it compared to writing your own FFT library or using one of the many other C or C++ FFT libraries and porting it to a GPU. You can always do a porting task. You can always reimplement from scratch. You can always do a porting task. The expectation, the assumption is that by using that library, you'd get likely significantly better performance than trying to do so yourself. That's true for almost all of the sparse and dense neural networks, for all the linear algebra. Uh, for the most part, for the common HPC tasks that people are using these GPUs for, you're going to find pretty good support for those type of tasks inherent with the library. So the trade-off is always, can I get this library to link properly, and can I understand the API or the headers for that library? Is that less time than the time it takes to reimplement it myself? In this case, the answer is generally yes. And so while you see all these possible options here, different support levels, and there's a huge compatibility matrix of this library works with this compute version on this particular platform, all that can be a little bit annoying. But generally, in at least your first usage cases, you'd be targeting one particular platform. And so you don't need the entire compatibility matrix. You need one column or one row of that compatibility matrix, and you'll be okay. You'll be able to look at, okay, this is a Jetson platform we're using, AGX Jetson platform. It's for an embedded computer vision application. Yes, you can roll all those libraries out entirely yourself. You don't need to, though. First off, the OpenCV libraries themselves would have CUDA ports to the fundamental functionality in there. And then on top of that, you could use any of the provided NVIDIA libraries, and you can get pretty good performance back out. I mean, that's true in general in life, I think, as a programmer, right? Uh, the reason we can be more effective in certain programming frameworks than others sometimes has something to do with syntax, but it generally in practice more so due to what is provided in the standard library, what's baked into the assumptions of the syntax or of the language that you've chosen. And if it's something that's not in a standard provided library, how hard is it to add more functionality that's not in the standard library? How hard is it to grab this piece of functionality needed to add to your project, right? In a C project, it's a pain. You have to use CMake or Make or one of 15 other build environments. And when it works, it's great. When it doesn't work, it's really quite awful. In Python, it's import, and import just kind of magically works. And maybe you have to install a package, and it all takes a few seconds. Different languages and frameworks take different approaches to it. NVIDIA's, at least for their own libraries, it's all kind of baked into the SDK. You install the software development kit for your particular platform. You get all that, so you should generally use it because it's all basically there for you. Briefly talk about memory management and what that looks like, just as an example of both some of the utility functions you can use and as well as just the built-in runtime functions that are there. Um, a lot of them look very similar to conventional standard C library functions. So, for example, we're used to using malloc. Well, there is a CUDA malloc. It looks kind of similar, but there is a distinction, right? If you recall what malloc looks like, it provides a pointer, right? And we're generating a pointer at the result of malloc. So it returns a pointer. Whereas CUDA malloc, actually, you pass it a pointer to a pointer. So the pointer is already allocated. You're then passing a reference to that pointer, and you're getting an overriding. We're actually modifying that pointer back out based on the number of bytes you are allocating. There's, like regular memset, there's also then CUDA memset. It does exactly what you would expect, right? Sets a region of memory on the device. All the standard memory management functions in C that we've kind of taken for granted that you've learned since you were a first year student here or before, they all exist with a CUDA version of it, for which sometimes the interface is very slightly different, other times it's exactly the same. Sometimes there's a capitalization where there isn't in the standard library version of the same, but it's all effectively doing the same thing. We do just have to be a little bit more explicit with how we're managing pointers because, and we'll talk about this in a moment, it's not as straightforward, right? We still, even with a unified memory model, we still may have two different copies of things executing, right? We have the CPU and we have the GPU, and that's always the case. We have both in our system, whether it's a very tiny CPU and a massive GPU, or vice versa, or they're roughly equal in size and importance to our application. So we are often going to have two copies of our objects that we're allocating in memory. It seems kind of wasteful, and maybe arguably it is sort of wasteful, but that's the fundamental coprocessor view of memory. We have our CPU that we would potentially be doing traditional mallocs on. We're going to allocate things, or whatever our memory management is. We're going to allocate things because the CPU has to do some work. Maybe the CPU is reading from a file, grabbing entries from the database, populating that memory to begin with, doing that initialization. Then we're going to want to copy that over to the device. So at least in the CUDA pre-unified memory model here, we would then separately also have to have our regular mallocs and our CUDA mallocs here. Regular malloc, CPU does its job, possibly initialization, but maybe more than that. There could be some tasks that are very well suited to staying on the CPU. When it's ready and it's time for us to actually then do some work on the GPU, we have to have that explicit copy operation here. So down here is just an example of using malloc and memset, and there's a problem with this. This would cause a crash. What's the problem that we have here in this example? Very trivial problem, but a problem nonetheless. People are here. It's trivial. Team 4 on the couch. Okay, thanks, Micah. Yes. That's right. So, in general, and I think that I call it a trivial bug. You haven't done this before, but there's going to be a very clear pattern where we're doing CUDA stuff. That's our GPU memory management. If we're doing no prefix of CUDA, that's our CPU side memory management. That's the big issue here. So CUDA malloc is okay. If we wanted to allocate something correct in red, and we wanted to allocate something and then set it to 0, which is what that code was trying to do, we would just use the CUDA version of the same. That would give you a segfault in the previous example if you just had a memset, because you would have this pointer that gets returned. And I think, our lab infrastructure has given us even maybe a deeper understanding of that pointers are not magic, right? Pointers are just addresses. And for our GPU in our lab, pointers are whatever we choose them to be, right? We have a starting address that for our physical layout of addresses makes sense to us, and everything is just relative to that. So pointers are just addresses. So CUDA malloc is the same concept. Memory allocation is a bit more complicated than how we do it in our lab infrastructure. You want to be efficient with your memory. You want to only allocate as much as needed and be able to remove entries relatively efficiently. We don't do any of that. We just kind of grow memory, and then if we run out of memory, we just give up, right? But so it's a little bit more complicated than that. But ultimately, what you get back is just a pointer. It's just an address. We have an address, and it's an address if it's a CUDA malloc that at least pre-unified memory model, and I'll stop saying that, but pre that relatively recent unified memory model is only relevant that address for the GPU. That D underscore A is a 32 or 64 bit value that is meaningless to the CPU. So if we try to do a memset on it, syntactically it's valid. Memset takes a pointer, we pass it a pointer. Compiler, no compiler that I'm aware of would raise any issue with you doing that, but it would just crash because then that D underscore A, as you try to do a memset on it, would presumably crash because that would correspond to some region in memory starting with that arbitrary 32 or 64 bit value that wouldn't mean anything to the CPU. We wouldn't have allocated anything in that region of memory. We're talking memory management units. We're talking our operating system catching that and causing there to be a seg fault or other type of crash. It's a relatively easy error to avoid. I think what's different is just the thought process of I'm managing potentially two separate regions of memory, maybe identically sized, but two separate regions of memory simultaneously. You're doing 2x the memory management when you're doing CUDA code. And for better or for worse, unfortunately, sometimes 3x the memory management. So there's explicit functions to do that copying for you. Um, if we have a relatively recent device and compute model, we actually can just do CUDA mallocs, and that pointer can generally work on the CPU side. The copying operations are still happening. So there's still performance implications. When we talk about unified memory, we're talking about a programmer's view of an address space. There are some devices in which the memory itself is also physically shared between the CPU and GPU. But today, still the general use case, that is not the case. That there is a physical DRAM for CPU and a physical DRAM for GPU. And so while we have a programmer's view that allows us to kind of ignore things like explicit memcopy functions, underneath the hood in the driver space, those copies are still happening. Possibly the driver can be more clever about it than we can. It may be smart enough to recognize, well, we allocated this region. We're only mem copying a small amount of it right now, and so we can be more effective and perhaps copy the whole thing even though it wasn't asked, or even save memory and not copy the whole amount. It can possibly do a better job of it than we can from a performance perspective, but physically the same instancing is happening. So while these explicit mem copy calls are somewhat deprecated, I'd be careful with that. It's still very much in common use. You look at the 2021 version of the CUDA SDK, and these CUDA mem copy calls are still completely used throughout it. But you have a destination and you have a source. So you have a CPU pointer and a GPU pointer. So it's a little different where we would normally use mem copy and have a CPU and a CPU pointer. Otherwise, it's basically the same, copying a number of bytes based on those pointers. We just have that separate little flag that tells us, oh, which direction is this copy going from? So you do have to be just a little bit more careful. The nice thing is our flow is usually so traditional. CPU malloc, CUDA malloc. CPU CUDA mem copy from CUDA mem copy hosted device, launch kernel, do a CUDA mem copy back, do all your frees. So that kind of boilerplate memory management gets you very far. It gets you most of the way there for common applications. Um, yeah, I mean, so pointers are just pointers, though, Nathan. So, you know that as well as anyone, right? So you need to have some mechanism to keep track of it. They could have syntactically uh, referred to it as something else. I had to think about that a little bit. Yeah, they could have been very C++y and wrapped it around a GPU pointer type of safe pointer, what could have prevented some sort of programmer errors, or it could give the compiler more insight as to what was happening there. The tricky part is that ultimately, for most CUDA code, we're dealing with the same exact types, from CPU to GPU. Whether that's the tricky part or whether that makes it doable or more manageable for us, we're dealing with the same kind of type. So you'll have this array of floats being copied to become this array of floats on the device, and then copying those back out. That's what makes it manageable. You don't have a lot of explicit conversion functions that are needed because, at least for compute mode, everything is roughly the same data types as what we're used to. So, in terms of the memory managed for this, I kind of gave the answer, but let's talk about this a little bit. So, let's assume we were doing matrix matrix multiplication, which is the example I want to get to today, um, where you have A and you have B of that side, and you want to do of that size, and you want to do matrix matrix multiplication on the device on the GPU. That'd be the whole point of this example. So we have some C code declares float A, float B of those particular sizes. We could do it with arbitrary sizes. I think it's more tractable with fixed predefined constant sizes there. So we do some stack based memory allocation potentially for the matrices, and we have some function that initializes create random matrix A, create random matrix B. What calls would we then need to do? What kind of memory management would we be required to do? Right. So the CPU malloc is already done. Right. I guess it's already kind of statically allocated for us. We would have to then do upwards, I think, of three CUDA malloc calls. Right. What's not shown here is the C. Right. So we have A and we have B. We also have to then be aware that these are inputs to what would be a kernel for doing the matrix matrix multiplication. We'd also need to keep track of the outputs as well. That would also be the case if this was just all host side. But now that it's device side, and I think you've got it, Matt. You've done this before, I take it. Uh, you would have to explicitly allocate whatever that 25 times 25 floats would be with a CUDA malloc for A, 25 times 30 times size of float for matrix B, and then for C, which would also be 25 times 30, you would have to allocate that many bytes also with a CUDA malloc. We would then have to have some sort of CUDA mem copy, like shown on the previous slide, of copying for those pointers from A, and it looks like A would be the second input to that CUDA mem copy. From device A is the first input to from host A to device A, that many number of bytes. Doing the same for B as well. We would then be able to run our kernel. We'll talk about the syntax for that in just a moment here. And then there'd have to be a CUDA mem copy back from device C to host C. So at some point, and statically probably would make sense for this example as well, we would need to have that allocated object C on the host side as well. So that's what I mean when I talk about like kind of 2x the memory management. I think if you have a feel for what you're doing in C already, this type of syntax won't overwhelm you. This won't be the reason that you're having trouble with CUDA, but it is 2x the amount of thought that you have to do with regards to what's happening. So there's our kernel syntax. We had already talked about this when we were getting started. Generally, our inputs are going to be pointers. For that reason, right? We're writing each kernel from an individual thread's perspective, and the way we isolate work tends to be by calculating unique offsets into arrays of memory. So for the matrix example, it would be a 2D array generally, and so it'd be a 2D block we'd be chunking off for each individual thread. But for the 1D case, it's also the same. Every thread would then have its input the same base address, the same pointer. What then happens as it's executing is we assign these unique IDs, these indices, to each of the threads based on our multidimensional layout of threads in our thread grid here. And we would use that index, that unique ID, to determine what piece of work is unique for that unique thread. Otherwise, syntactically, we specify global to indicate that to the compiler that this is going to be run on the device and not on the host. You can have functions that are both. That can be compiled both for native host code for your x86 processor as well as in CUDA for your NVIDIA processor. And some more deep C++ conversation going on. Nathan's in his wheelhouse. I'm going to let you keep going. That's fine. So you have global, you have device. and then you have host, and you can also basically effectively overload the function qualifiers. That's just a little, uh, inner workings of how the NVCC compiler works. No, you can continue, Nathan. Please, you're fine. Uh, Works to very easily basically tag functions so that it knows either way you're writing what is effectively C code with some C++isms thrown in. It has to be able to detect when it's compiling what is it actually targeting, and that's what those function qualifiers are being used for. Our kernel launch is definitely something that isn't exactly either C or C++ looking, and so this would be the one unique thing that a syntax highlighter would have to be able to recognize. This is why we can't just use GCC to compile these kernels for us, or this CUDA code for us, but we're specifying what at first glance looks something like a function call, because our kernels do have function call style inputs, those pointers, maybe some constants. And then inside those sort of triple brackets we have here, we're specifying potentially up to three things. In this example, we're just showing two. We're specifying the dimensions of our block, our threads inside our block, and our dimensions of block inside a grid. So a dim3 is like those vec3s we've been using throughout, three-dimensional variables here. So they don't have to use all three dimensions. You can have your either grid dimension or block dimension be just a single int, a single scalar value, or you declare it as a dim3 and you can just declare it to actually be um, use two of those dimensions. So the example shown there in the middle is using that built-in dim3 type, but only actually using two of those three dimensions. Presumably the third dimension gets initialized as 1, and that's what the compiler would do for you. But here we'd be specifying that we'd have a 25 cross 25 block of threads, and then a 16 cross 16 block of those blocks in a grid. So the total number of threads would be 25 times 25, or 25 squared times 16 squared, total number of threads being launched on the device. That's an arbitrary choice. All of these are kind of arbitrary choice. We talked about on Tuesday, and this is a fundamental distinction here, is that we can assume that all the threads in a given block are executing on the same SM and roughly at the same time. They get composed or decomposed down into these warps, 32 threads at a given time. Those are the ones that are truly executing concurrently. But by and large, all the threads in a given block are put on an SM at a given time. We looked at that occupancy calculator, and one of our goals, although occupancy is not the same as performance, one of our goals is to improve our occupancy, get more threads executing at the same time, a better chance of hiding memory latency, presumably. But this is an important distinction. All of those threads in a block are executing concurrently. You write those threads in a block as if it's all happening at the same time. If you need to synchronize, if you need to pause and wait for other threads to catch up, you have to explicitly add those synchronization mechanisms into the kernel written from the block's perspective. It's doable. There's a single sync threads primitive that gives you exactly that functionality. It's a barrier like any other barrier call, but there's performance implications of doing that. So synchronization is usually a fairly expensive thing to do. Some threads could be falling behind, some warps could be falling behind others. We lose some of the benefit of having parallel execution if we're serializing, and that's a natural thing. And then for blocks within that grid, those 256 blocks we have inside our 16 by 16 grid here, there's some presumable rationality to how these things get ordered and allocated to being launched on the SMs. But in general, from the kernel's perspective and from the individual thread's perspective, we have no say in terms of what order those are executed on. They won't necessarily be on the same device or the same SM in a given device. The order in which they will happen is not that clear. Presumably, it'll be next one available. So for the next SM that is free to take another block because a previous block has finished, presumably it'll go in some reasonable scan order of 0, 0, then 0, 1, then 0, 2. But nowhere does it guarantee that that's the case. So that does require a different level of parallelism in your implementation. The thread blocks, you can assume all those threads are working together in relative lockstep to each other. Some threads will get somewhat further ahead than others, but they're in relative lockstep. You can ensure they're in total lockstep by doing an explicit synchronization call. With regards to threads that are in different blocks, you have to be very careful how you write those. You can't expect one to have made a certain amount of progress by the time the next one launches. So you have to have ultimately a different level of parallelism in your code to take advantage of multiple blocks. Syntactically, then, that example here on the bottom is also valid. If you just have a 1D array of threads in a block and a 1D array of blocks in a grid, you can also use those dim3 types. That will also work, but you don't need to. You can also just use integers as the actual input to your kernel invocation here. So we got some of those. So there's now the dim3 type, which we're providing as an input. And even if we only provide two of those three dimensions, the assumption I think you can make is that it would get promoted to a third dimension. You provided a scale, you provided an integer, it'll get promoted that 32 to 32 comma 1 comma 1 as a dim3 type here. Then within each kernel itself that are written from the threads and individual threads perspective, the challenge I would think of doing CUDA in my perspective is this part is keeping track of which thread am I based on the automatically assigned thread invocation, kernel invocation variables that are provided to you that you can assume are assigned as part of that workload assignment of that hardware task scheduler in part is doing this assignment of letting each thread know which one you are. But that is a multi-dimensional thing. It can get a little bit hairy here if we're not careful. We need to know first off the size of our kernel launch, how many blocks there are, what's the size of each block, and both of those can be three-dimensional things. And then that's a constant across the entire kernel launch. Then now on a thread by thread basis, we need to know which one we are. And that's two pieces of information we need to know. We need to know inside the block which thread am I. It could be three-dimensional, it could be one-dimensional here. Which one am I? That's our thread index. That's that one at the bottom here. And then potentially, depending on how we write our code, if we have this multi-dimensional grid of blocks, we then also need to know, well, which block am I also in? I need to know where I'm inside each block and then which block I happen to be. For our 25, times 25 thread layout in a block, that value of thread index would have a .x and a .y between 0 and 24. Likewise, the block index would have a .x and a .y between 0 and 15. So what you wind up seeing is a lot of code that looks very similar to some of the two-dimensional to one-dimensional memory layout stuff. You had to do a little bit of that in 381. We've been doing a little bit of that this semester as well, which is going from an image or a frame buffer or just a two-dimensional, or in this case, unfortunately, three-dimensional data structure and serializing it back out or converting it to a one-dimensional equivalent of it. And that's you do it once or twice and then it's not so bad, but it's a little bit different than what you would typically have to write in your code because generally the whole point of having these indices is again to say I have a pointer as an input to my kernel. From this thread's perspective, there's one or a finite amount of work that this individual thread should be doing before it completes. We can move on to the next block. Where is that work? What should my pointer, and generally it's going to be a one-dimensional pointer. It doesn't have to be, but generally it will be. Where is my pointer? Where's my offset into that pointer based on what the individual thread indices are, the block indices, and then the actual dimensions of the kernel launch that we would have. That is kind of ugly. I mean, in terms of representing it, in terms of visualizing it, it's beyond my ability to actually visualize and conceptualize anything more than 3 dimensions, to be honest, right? Whereas we can have up to 9 dimensions here. Each block can have up to 3 dimensions. So thread index.xyz. Okay, so far so good. But then within terms of our blocks within a grid, each of those can also have 3 dimensions. Those are xyz. That multiplies. That doesn't add together. So technically, if we were to try to visualize this, it would become a 9-dimensional layout. And how do we represent that one-dimensional array of data when using an array of blocks in the 9-dimensional case? Well, I can't do that. At least I can't draw it out and visualize it. But for the 3-dimensional case, we can do it. Everyone can see this okay here, right? We know, I think, how to do it on the 2-dimensional case because actually this semester and even in 381, you do that a lot, right? Anytime you're working from an image data or a buffer data and you're trying to figure out what should my next pointer be. We're doing this in hardware as well, right? Lots of mistakes along the way because we forget byte offsets and things like that. That's just a constant factor here and isn't germane to this analysis. But the code that we'd have would look very similar here. So if this was a single block of threads, let's ignore the grid for now. I can't get up to 9 dimensions without losing a little bit of my sanity here. And we are interested in knowing for this particular dot x and dot y, what that serializes out to, then we need to know those dimensions. We would need to then know what, and it's the block dimension here. What is our block dimension dot x, and potentially, as we'll see in a moment here, what our block dimension dot y is. Right? Think back to our render output code or even the driver code. When we want to figure out what our offset is into memory, or in this case, it's basically the same. Given a thread index, what our offset is into memory, we have to know what our stride length is, right? We have to know when I go from one row to the next row in a row major order of our memory, what is that offset corresponding to? And the math is something that we've seen, time and time again. Then, so our actual index would be, we'll call this like our global index would be something like in this two-dimensional case equals, and this is that thread index built in that is provided for us. It would be the thread index. How much off are we in the y dimension in our rows case here? And to be honest, which one is row and which one is column doesn't really matter as long as we're consistent as we're doing it, right? Unlike when doing sort of that pointer arithmetic, issues of row major and column major order, well, that's kind of entirely for us to determine here. Doing it the exact opposite way may or may not lead to any different results in terms of the parallelism and the actual resulting performance. But this kind of math is the kind of thing we'll see. This kind of bookkeeping, you'll see this over and over again, even for this simple two-dimensional case. Each time we go down a row here, we're adding a whole block dimension .x into our offset. So we're multiplying those two together. If I'm at row 0, it's just the offset in the x dimension. Otherwise, I do that multiplication and I add the .x to it. We've seen that a lot, right? With our I and our j, where we sometimes saw some problems with semesters, we forget to multiply by 4 if it's byte addressable, but that's not what we're doing here. We are determining a good offset into a pointer for that two-dimensional case. And that's what this is doing here. We don't as often, at least for the kind of code we've been writing, for the last few semesters together, we don't often do 3 dimensions, but we can. And if we want to get enough, close enough. If we want to get enough threads out here, we have to start looking at 3-dimensional breakdowns of threads inside of, that's supposed to be a cube, it's close enough. And it's the same concept, but now we also have this additional dimension. And this would be, I'm going to write this as bd.z here, just for shorthand here. That offset into that two-dimensional kind of square there, that math is still valid, right? That is the offset, the index into just a two-dimensional square. That is our offset into 1. That's assuming z equals 0. Well, now what happens when z is no longer equal to 0? This offset into this is actually now just an offset into one of those, if you want to think of them as matrix planes here, as bit planes and a multi-dimensional object here, but it's just our offset into a single one of these squares in one dimension or in 2 dimensions as we go now into the 3rd dimension. Now we have to take that z into account. If z is 0, or would be 1 in this case, we're fine. But we would have to take that entire thing now as we go from z equals 0 to z equals 1 and multiply that together by what that offset would be. And that would be our block dim x and our block dim y. That entire thing multiplied by that, right? As times our actual offset. When z equals 0, it's the same as before. and that would need to be a plus there, right? When z is 0, it would be the same as before. It's our offset in this. When z equals 1, it's that same exact relative offset, and now we're a whole square further away. So we would just be continuing that pattern. So logically, it's fine. Conceptually, it's kind of hard to really just keep track of. Ultimately, generally, at least in these examples, we have these pointers: multiple input pointers, multiple output pointers, and the kernel's written from a single thread's perspective. So a big chunk of the CUDA code is that kind of initial boilerplate, both for reading input and calculating output, which is figuring out this is true in the general case. For your particular application, it doesn't have to be necessarily just a single value we're reading. You could take this global index and use it to read a whole range of values. Only the most trivial examples have just like a pure one-to-one relationship between input and output. Life gets messier than that very quickly. But calculating that kind of global index, and this is just for a single thread inside a block, right? Um, is a very common thing you will see, and you'll see some piece of code like that in the beginning of almost every conventional CUDA call. And that was the 3D to 1D solution. Now, if we look at what it means to go from 9 dimensions down to 1 dimension, it is just more of the same. But now we're first figuring out which block am I. So, assuming I didn't screw that up terribly in that example, I believe this is correct. But now it's you could start from either direction or the other. But now, which block am I inside my grid? If that's 3 dimensions, the math is exactly the same. Just using now the block index and the grid dimensions versus the thread index and the block dimensions. We could have drawn that same exact example and just said this was a grid and not an individual block. The math is exactly the same. I would hate to say that I did it wrong. Looks close enough. If it's wrong, it's very slightly intentionally wrong. I believe it's fine. So that math is still. I put my parentheses somewhere different, but it's the same exact math that we have. And then we have to figure out, given that block ID, where am I inside my thread, or where is my thread inside the space of all threads? And that gets to our 9 dimensions there, right? Because we have our block ID in our 3 dimensional space. Now we have exactly what we had before, which is our thread ID inside our 3 dimensional block. So where's our thread ID in our 9 dimensional grid would be those two things multiplied together. So as we go from one block in a grid to the next one, we would have that particular offset inside the grid and then added to that offset inside the particular block. That's a lot to keep track of. And so I think the challenge of this is, recognizing some of the limitations of how we can, first off, lay out our memory, how we can extract parallelism back out, and how we can generate enough threads that have meaningful work to do with that kind of layout. So that common pattern of 2D mapping to 1D is what we're just doing over and over here. Lost it. Okay. Simple example is just incrementing array elements by some constant amount. The CPU version of it is kind of trivial, but that's fine. We'll start with something basic. Takes as input a pointer, A, an array, and a constant to increment. B also provides the length information. So we iterate through a loop of 0 to n, and we just do an incrementing of that array given our offset into the array labeled as index there. That's a pretty traditional, CPU or C program for doing the same. Our GPU program isn't going to look that different, but what's really different about the GPU program is, again, well, what kind of parallelism can we take back out? And the answer is a lot, right? There's an embarrassing level of parallelism here. As many threads as we can throw at the problem, those threads are going to be allowed to execute concurrently, or could be allowed to execute concurrently, because going from A of 0 to A of 1, there's no dependency between the two. So, of course, yes, there's a lot of optimizations we can make to the CPU program here. But from the GPU's perspective, we're limited more by just our total occupancy calculation. For that particular device that we're executing this on, we would have to figure out, what is the right block and grid size to get a reasonable number of parallel threads. No, so in this case, block size would have been just some variable that we would have had to decide that is appropriate for us. The limiting factor on this is one of two things. So there are some physical limits. If you go back to that spreadsheet for this compute capability, here's how big your blocks can get, and we talked about that. There's probably some registers somewhere implemented in hardware that worked just fine when it was 8 bits, and when they tried to make it 9 bits, it wasn't worth the extra trouble to meet timing and to deal with all of that. Um, but having then said that, the real limitation of this particular example is n, right? We don't know what n is, and so n could be extremely large. But in this case, the individual tasks to do that incrementing of each element of A are entirely parallel from each other, but there's just n total bits of work or n total pieces of work to be done here. So while we can allocate as many threads as our occupancy spreadsheet tells us we're allowed to do for this example, it may be using a register. I don't know, maybe not. Maybe one register to store that index value, maybe two registers to store the intermediate computation here. We could probably fill a whole ton of threads depending on what device we have here. The total number of threads is limited by the total amount of parallel work, which at least for this example is presumably n. Um, so it's a little abstract in that I don't say exactly what the block size here is, but given a block size, which in this case would be one dimensional, right? Because it's just an integer here, we're limited by, well, for a given block size, let's say it's 1024, our grid size, which is also just an integer here, so it's a 1D grid size, is limited by n divided by that value, right? If you have 64K elements and our block size is going to our block is going to handle 1024 of them at a time or 1K of them at a time, our grid size shouldn't be any larger than 64. And it's not a matter of not being able to get more parallelism. There's just only so much work to be done, right? So in this case, yeah, there has to still be some of the work to do an explicit copy. Whether it makes sense to actually run this code on the GPU is not something we can actually answer just by looking at it. You may say, well, obviously this makes sense on the GPU. There's 64K elements in an array, and we're able to do all 64K of them in parallel. Well, it's not truly in parallel. It depends on the device, depends on how many blocks we can fit on the device at any given time. We would then have to sequentialize those that aren't able to be executed concurrently. And what the code that's not shown here, your CUDA malloc, your CUDA memcopy, we have a lot of bandwidth available, but it's not an infinite amount of bandwidth. There's a penalty associated with doing that initial copy. So we have to be aware of that as well, right? So we have to figure out, well, for this application, does it make sense? It's really a matter of, is the overhead of managing all these GPU resources and of doing the copy, uh, is it less so significant? I would say significantly less so the overhead or the benefits gained by doing this addition in parallel on a GPU versus just keeping on everything on the CPU and optimizing a little bit more of that CPU code there. So you generally can't look at an application and say, yes, this application makes sense on a GPU by looking at the code, right? No matter how much parallelism you're able to find, you can't find any more than this, right? Every little piece of work is entirely parallel of the next piece of work. Is it worth it? It's hard to say. We can get thousands of threads. You can get n total threads without any difficulty here. Is it faster? Well, it's hard to say here. Um, and Micah, your question is a good one. I mentioned it briefly on Tuesday, although I didn't show examples of that code. The same exact thing we can do via our spreadsheet, which is given a compute capability. The device I'll run this on is on 5.2 compute capability. Uh, Here are the hard upper limits, and then given your register usage and shared memory usage, here are the practical limits of how many threads and how large your blocks can be. Based on that, you can actually also do that in your CUDA code itself. And actually at launch time, query the compute capability. You'll see large segments of code for doing this. If I'm compute capability 3.1, do this. If I'm 5.2, do this. If et cetera, do this. And you'll see different invocations of those blocks um, based on which capability you happen to have for that particular device the code is running on. There's definitely a disadvantage, I think, in the CUDA world compared to just traditional C or C++ programming. Your compiler for traditional CPU programming takes care of so much of that for you. I mean, it's doing a lot of that stuff for you. There are built-in instructions on x86 microprocessors that tell you here's the capability of this device to some extent or the other, and a lot of that functionality can get baked in directly into the compiler to say, given this device, if it has this set of instructions, execute this block of code, otherwise execute this other more traditional block of code. At least as of right now, because our strategy for doing parallelization is so application specific, you have to write all that code yourself. You're writing a lot of boilerplate code or maybe copy pasting from existing examples, queries the device capability, determines what the right answer should be for this. It'll tell you what a valid answer is. It won't tell you what the right answer is from a performance perspective. If we want to know the right answer, I mean, we can reason about it. We have some understanding based on what we're learning today. We can reason about it at least to some extent. What is happening in the GPU and why it is a reasonable assumption to make regarding grid layout and block layout and things like that. The other thing we can do is we can always profile our applications. And we've lost our pipe here, so give me a second. We can profile our applications, and it will tell us how it's doing, telling us where it's getting stuck in CUDA calls, tell us where it's getting stuck in the actual kernel invocation, tell us how effectively the kernel allocation is actually being. Mm, One second here. I have to run this as root, and this is going to fail. Let's see. So they actually provide a nice visual profiler. Yeah, yeah, yeah. This is perfectly appropriate today that this is failing on us here. Hold on. After having made it so long without failing, you don't need to see all my fails here. Uh, 1 second. Well, that is a shame. So I'm not going to be able to show you that today. I'm having some SSH forwarding issues. And we don't have to use SSH. We have this wonderful, not at all horribly slow remote connection to the machine. Next spring, we won't be dealing with this at all. Life will be so much simpler for us. Um, so here's just an example that I brought up that has sufficiently complicated kernel. See if it'll actually load up here. NVIDIA Visual Profiler. There's a lot of things you can check with it. Some of them wouldn't be super relevant for this example. OpenACC wouldn't do anything. There is not an interesting thread trace here. Basically grabbing everything that'll let me grab. So it just runs it. And like any profiler, we've seen in previous classes using command line profilers, and there's a number of utilities. This is primarily the only one that works for us in doing CUDA programming, and it does tell you for your given application, where are the driver calls taking place, how much time is being spent in them. Likewise for the kernel launches, and in this case, maybe I have to expand upon this a little bit. There's a number of different kernel calls that are being had. This is doing a discrete cosine transform. Just an example of something that's running multiple kernels. It's not really super important in and of itself. Where the time is being spent, what the overall overhead is of running this application. Well, A couple things. To start up, there's some driver API just starting up in the application. It's doing some of that just-in-time translation to actually get you the correct binary runtime for that particular application. So a little bit of driver magic. I think if we ran this a second time, we wouldn't have that little bit of overhead associated with it here. We can see in this case, and then I talked about this on the slide as well, right? The trade-off involved of whether it makes sense. What are you sharing with us here? Okay. Whether it makes sense to run this kernel or not. Are we getting enough benefit in terms of this parallelism that's available to us on the device or not? And the answer is it depends. You can only answer that question ultimately while we can reason about it. Uh, Thanks, Matt. You can reason about it, but we ultimately have to execute it. Now, doing this, Insight or the visual profiler doesn't actually answer that question for us either. It gives us insight, no pun intended, into how that execution is actually happening on the device, which can tell us a lot. In fact, this one actually does tell us a lot, right? This is an NVIDIA provided kernel that presumably is pretty well optimized. At least one poor intern over a summer had to write this as part of their experience to add to the SDK. It's doing DCT, so it's doing something processing on two-dimensional data. Lots of parallelism. Generally, there's a sliding window you apply to an image, and you can do those individual windows completely independently of the other windows. A lot of memory throughput would be needed, so it should take advantage of what the device happens. From a performance perspective, we can see something here. Or at least, there's a lot of things you could see here. There's all these kernels here. And maybe part of the issue is the kernels are just so efficient on this device that we hardly see them in the timeline. This x-axis here, this timeline is literally from 0 to 1 second, how things are executing on the Titan X, the Maxwell class hardware, GTX 200 or whatever it's called that I'm executing this on currently. These are the individual kernel launches down here. They're very tiny. In terms of how long they run, it's measured in microseconds. Well, what is taking our largest block of time here? CUDA malloc array. You say, well, it's a malloc. Why would malloc be taking any time at all? Malloc is a very there's some data structures it's keeping track of. The code itself is complicated, but the actual time it should take to allocate something should be pretty straightforward. Allocate space on the heap, return back a pointer. Why is that taking effectively more than all of the computation entirely for this code? Why do we think that'd be the case? Any thoughts? Matt, I'll ask you. Having played around with this a bit more than others. So yeah, absolutely. So the actual pointer manipulation is probably pretty trivial in terms of runtime here. I think we can make that assumption. The actual heap data structure or whatever is being done in the driver to keep track of, give me the next available free pointer for this many bytes that I'm requesting. This isn't showing, and this is using the more recent unified memory model. This isn't showing an explicit CUDA malloc followed by a CUDA mem copy. It's actually doing both under the hood. So this is doing a malloc of memory. It's also then explicitly going to be copying data over, given an input array to it. And that, as we're saying, for this example, we can't actually answer the question, was the GPU worth it or not? That's not answered by this. This does tell us that we have, via the kernels that have been written for this, given the parallelization strategy that is employed and the number of threads that were able to be executed on this particular device, we can at least say with some confidence we are memory bound. The time it takes to copy our data over is significantly longer than the actual time it takes to do the computation. That's not necessarily a good or a bad thing. It's a neutral stance. It's in terms of we've applied some optimization. We've hopefully transformed it from a compute bound problem to a memory bound problem. It's always bound by one or the other. I mean, it's either I/O or memory, or it's compute bound. You optimize one at the expense of the other, and you have a trade-off associated with it. Um, yeah, this will tell us some relatively simple things here with regards to this. Um, low mem copy kernel overlap. Well, I think we see that, right? I mean, okay, that is useful information here. There appears to be no mem copy kernel overlap. Doing mem copy and kernel overlap is a very difficult thing to do, right? Writing our kernel from an individual thread's perspective is already a little tricky. If we had to write it under the assumption that we don't know if our memory is valid yet, because the mem copy may still be happening, that is a very difficult thing to do. Usually, that overlap is achieved by mem copying for the next kernel launch while the current kernel launch is ongoing, and not attempting to actually overlap computation and copying of memory in the way we would traditionally think of it. Um, the multiprocessors of one or more GPUs is mostly idle. That doesn't seem great. So possibly for this, no, possibly for this application, um, we could have launched more threads. We could take a look at the source for it. Just give me a second here, and we can try to overwhelm it. This will take just a minute to bring up the source for that example. What else do we have going on? It is, of course, not a straightforward application here, but we can still bring it up and see what happens. This is the DCT 8x8 applications. This is going to take a little while, but let's see the actual kernel launch here. Where we have our grid size, which we may be able to provide as an input to this. Block size appears to be a constant provided in the code here. Well, live programming with Joe is not going to be a success today. We're not going to try it. But yeah, I think I had turned on for power usage as well. That should be one of the tabs that we would have here. Uh, it's in there somewhere. Um, but anyway, I think the more important point is going back to this question because we're not getting the experience this semester to actually do this ourselves, right? To really play around with it. There's plenty of hardware available to you on campus, and NVIDIA also provides some credits for students who want to explore more in GPU technology. And I can help you navigate that if you're interested in doing so. I know Matt has also offered that as a service to his fellow classmates, which is great. The answer to the question is whether this was worthwhile or not is not something you can really answer without having that fair comparison. This is true of any application acceleration, but it's equally true of GPU. Just because you can have block size times block size threads, where I can't figure out in the code where exactly that's defined, just because you have that many number of threads and you have a device that's capable of that many number of threads and you have a lot of parallelism in the application, that doesn't actually answer the question of whether the performance benefit was actually seen here. The true comparison, again, this tells you some bottlenecks. It tells me that I'm spending more time copying data over than I am actually doing my kernel launches here. It's giving me some hints regarding uh, kernels are kind of sitting around and the threads are sitting around and not doing as much parallel work as one would hope. The true comparison would have to be between this and an entirely CPU resident version of the code. And probably not one in where you just hit make and executed and timed it. One in which a comparable amount of time was spent, presumably, in doing that optimization, in looking at different parallelization strategies on the CPU, different SIMD and other extrinsics and intrinsic ways of allowing you to make use of the target hardware you're actually running on. Only when you've done that can you actually answer that question. Was the performance benefit seen there? This tells you some kind of relative analysis. Given this particular device with this particular application run with default options, there could have been a million flags on runtime I could have passed it that I didn't pass here. Here's what the performance profile looks like. Doesn't actually tell you anything other than that. It's useful insight if you're seeing that something is a lot less efficient than you would expect it to be. This can provide you that feedback. If you know your task is to run your code on a GPU, that is the task you are given. This is an extremely helpful tool in terms of getting the performance you expect back out. But to answer the question, was the performance acceleration worthwhile? That is a much more difficult question. This tool will not tell you that. It's not capable of telling you that. For better or for worse, today we have to kind of leave things here, and not just today. This semester we have to kind of leave things here. I said I wouldn't cry, and I won't. So anyway, it's been a blast. Ultimately, a little bit of a regret. I mean, this was great. I think in person it could be so much better. I know a lot of you are still going to be around on campus after this semester is over. Maybe not immediately right away. Maybe you'll be coming back to us in the fall or some future semester. You're always welcome to stop by my office when I start going back to the office. And I had hinted at, and I want this to be the case next spring, if you're still around, and this course is going again, and it'll be going in 2050 Cougar. I want everyone there. I want you guys to stop by on occasion, if to do nothing else other than just to nod your head and commiserate, uh, you know, point at an error on the screen and say, "Oh, I know what that error is," and then just quietly walk away. A little bit of guidance, a little bit of mentoring, a little bit of hazing as well, I think would be nice. Um, but it's been an experiment, right? Doing this in this online format, virtual format. I didn't know if it was going to work or not. It was only about 5 weeks in did I realize, okay, I think it's not going to completely fall on its face. We still have work left to do. I think the temptation is to say, well, we've survived the semester, going to study for exams and be done. Put in that final grind on your projects. I think you'll be proud of the effort that you put in, and we can't control for the results that we see here. These were all speculative projects with varying degrees of risk associated with them. We can't control whether or not you succeed. I get that. That's been the case for these other assignments, but for those I generally knew they would work or could work. For this one, for your projects, I don't know. And we're finding out together whether or not they will work. Um, but it's worth a try. It's definitely worth a shot. You'll feel so much better after next Thursday knowing that succeed or fail, you gave it a good faith, effort. You gave it a fair shot, and you won't be disappointed. I think in the outcome when that's the case. So finally, for the ultimately second to last time, but the last lecture time, let's leave it at here for today. And I'll see folks on Thursday or beforehand. Just ping me. We can chat about your projects. I, I don't want you to come talk to me and just if you're gonna, cry about the difficulty of your project. Let me help you in a specific way, but that's fine too. So anyway, until next Thursday, and it has been a pleasure. Um, Hope to see all of you at some point in the future in person. Thanks.